Welcome everybody. Thank you for joining us for the NSERC PermafrostNet seminar series. My name is Tristan McLean. I'm the Director of Operations for NSERC PermafrostNet. And today we have a presentation on the flood susceptibility assessment of the Hudson Bay Railway. I will be giving a little introduction to our speaker today, Adeleh, and then she'll take over and give us a presentation, after which we'll have time for a Q&A. You can ask all your questions. Feel free to put any questions during the presentation into the chat. So Adeleh is a Master of Applied Science student in Civil Engineering at Carleton University, where she began her studies in winter 2023. She completed her bachelor's degree in civil engineering at Amir Kabir University of Technology in Tehran in 2022, where she became interested in climate-related challenges affecting infrastructure. Motivated by a growing focus on climate change impacts in northern regions, Adeleh's research centers on cold region hydrology. Her work explores how thawing permafrost and shifts in snowmelt and rainfall patterns influence flood risk along the Hudson Bay Railway. So without further ado, over to you, Adeleh.
Hi everyone, I'm Adeleh, and thanks for being here today for this presentation. Today I will be presenting a summary of my master thesis about flood susceptibility assessment of the Hudson Bay Railway. This is a work that has been done at Carleton University under the supervision of Professor Sean Kenny from Department of Civil and Environmental Engineering, Professor Elis from Department of Civil Engineering from Queen's University, and Professor Weir River from Department of Geography and Environmental Studies from Carleton University. So climate change has influenced all regions around the world, but its impacts are more pronounced in Arctic and subarctic regions. We might have heard these sentences that Arctic temperatures are rising at twice the global average or 4 times the global average. And this rapid amplified climate change has a significant effect on the cold region basins environment. First of all, it can change their nival hydrological regime. In these basins, usually the major part of the precipitation falls as snow. It is stored in the snowpack during the winter and then released to the river system during this short time of the snow melt period. But this regime has been changing due to the higher temperatures, and there are some projections that saying this snowfall dominated winters are transferring to some extended rainy seasons by the end of 21st centuries. Also, higher temperatures during winter and the spring means we might see earlier or higher spring freshet in some of these basins. Also, higher temperature means that the moisture holding capacity of the atmosphere is increasing, and we might see more frequent intense rainfall and snowfall events. Beside all of these hydrological changes, the landscape is changing. We have permafrost degradation, which means that we can see the transition from those elevated frozen peat plateaus to some collapsed wetlands. This can change the whole connectivity between surface and subsurface water, and we can see new surface and subsurface water pathways. And all of these can change the basin's storage capacity and the timing and magnitude of peak flows in the river systems of this area. All of these environmental changes can have devastating effect on the linear infrastructure in this area, and it can make the construction and management of this infrastructure challenging. One of the examples of this linear infrastructure is Hudson Bay Railway, which has faced the climate change effect during its operational lifetime. This is an 821-kilometer route in northern Manitoba, which passes through different types of permafrost zones and connects the path to the port of Churchill. Since its construction in 1929, the maintenance of this railway has been always challenging due to permafrost degradation, the ice-rich subgrade permafrost degradation. As a result of this toss settlement, we can see some differential settlement along the route, and as the HBR crew sometimes says, we can see the recurrence of sinkholes. The nature of these sinkholes, the number of them, and even the mitigation methods that can control the occurrence of these sinkholes have been the topics for several studies since 1970s in this area. This permafrost degradation and thaw settlement was not the only natural hazard that this railway is facing due to the climate change. The other one, which has been less studied in this area, are extreme events and specifically flooding events and resulted washouts and overtoppings. So this railway is traversing a relatively flat terrain, and this flat terrain is restricting the surface drainage, promote peat accumulation, and wetland development. As a result of this poor drainage, and as you can see here, this very dense drainage network, it is common to see thousands of water bodies surrounding the railway corridor. In such an inundated and wet environment, the water management system of this railway has a critical role to channel the runoff through its natural pathways and prevent overtopping of the embankment. But despite this critical role, limited information is available about the performance of this water management system under current and future climate conditions. Also, during the past decade, we had some extreme events in this area. We saw an unprecedented flooding event in the spring of 2017, which resulted in several unstable and washouts areas between Gillam and Churchill. So in this study, we were trying to answer two main questions about this natural hazard. The first one was, where are the locations along the HBR that are most susceptible to flooding? This was a study that has been done on the 15 basins along the railway, and to answer this question, a simple mapping techniques and GIS analysis has been used. In the second part, we chose one of those more susceptible basins along the railway and developed a hydrological model for this basin to answer the second question, which was how effective is the railway water management system in these flood-prone areas. Before talking about these two studies, I will give a quick overview about the study area. The region around this Hudson Bay Railway consists of mosaics of wetlands and uplands. And as we go northward to Hudson Bay lowland, the coverage of this wetlands increases, and the basins here in the Hudson Bay lowland have the wetland coverage of more than 50%. The predominant wetland type in these areas are peatlands, fens, and bogs with peat accumulation more than 40 centimeters. We can see different vegetation in the uplands and wetlands. In uplands, it's common to see black sparrows or African jack pine with a thick peat layer on the ground with sphagnum mosses and lichens. And in wetlands, we see, specifically fens, we see shrubs and sedge. The main mineral soil type in the southern part, in boreal shield and boreal plain part, is glacial lacustrine deposits, and this changes to glacial marine in the Hudson Bay lowland area. The thickness of this mineral soil is changing between 1 meter and 20 meter along the railway, and on the top of this mineral soil, we have a thick layer of peat, especially in the Hudson Bay lowland part. And the thickness of this peat layer decreases as we go to the coastal zone and increases in inland near the boreal plain. The common peat thickness is around 50 and 150 centimeter, and the maximum peat thickness is about 550 centimeter. And as I mentioned, the whole railway is on permafrost, but this permafrost has a northward growing pattern. So we have no permafrost in the southern part, and then in the northern part, we have a continuous permafrost. And this northward growing pattern is the same for excess ground ice content, and we have the highest volumes here in Churchill. So with this introduction, in the next few slides, I will talk about the first part of the study, which was about flood susceptibility mapping. I first gave an introduction about the conceptual framework behind the mapping, then the methodology, the steps in methodology, what are the parameters in the map, and how I reclassified these layers and overlaid them. And then I will discuss the result, the final susceptibility map, and also the limitations. So this GIS analysis are some of the initial type of analysis that people usually do in every single flood prevention and mitigation study. But for developing these type of flood susceptibility maps, we need to know what are the most important parameters that can increase the amount of runoff or the risk of flood. Normally, people consider some parameters like slope, elevation, soil type, vegetation, and land cover. But these type of parameters can be different for a cold region, wetland-dominated basin. The predominant land color here is different types of peatlands. So the parameters that we want to choose here should reflect the specific characteristics of these basins and the specific hydrological response of this landscape, these different types of land cover. So here we have peat plateaus, which are peatlands that have permafrost underneath. They usually have higher topography, so they can redirect runoff to the surrounding environment, and they usually generate significant amount of runoff during the snowmelt season. The next type are bogs, which usually happen in depression. They have a water table below the surface, so they receive runoff from the surrounding environment, but they're not capable of discharging it to these peat plateaus around. And the third one was fens, which were common in this area. And again, these happen in depression, they have lower topography, but they are actually a main part of the river network. So they are conveyors of flow and they can increase the amount of runoff. So with this conceptual framework, the first two initial layers have been prepared. The first one was percentage area of bogs, and this was calculated for all the 15 basins along the railway. And as you can see here, these basins north of Lalage all have a bogs percentage area more than 15%. Fence percentage area was the next layer, and this could increase the amount of runoff, and this had the highest values for this section of the track between O'Day and Belcher, and also a small section in Rocasco. The third layer was drainage density, which is the total stream length per unit area, and this was calculated here based on NHN, Natural Hydro Network. This map showed that the section of the track between Lalage and Chesney had a higher drainage density, more than 1.6 kilometer per square kilometer, and the highest values were found between O'Day and Belcher. In the final map or parameter, I wanted to consider the effect of frozen ground, impermeable ground that can significantly increase the amount of runoff. But in the absence of layers about the location of peat plateaus or permafrost, I used this ground excess ice content map. And this layer showed that every section of the track north of Gillam is located on a ground with high to very high excess ice content. After preparing those initial layers, they have been reclassified to the indexes from 1 to 5, 1 showing lowest susceptibility, 5 showing highest susceptibility. In this reclassifying, the highest values of fen percentage area, drainage density, and ice map content were assigned to the higher flood susceptibility, where this was the opposite for bog percentage area. And for this one, the higher percentage area of bogs were assigned to lower flood susceptibility. Then these layers were overlaid with equal weights to calculate the final susceptibility index. This equal weighting method was just the starting point in this study, and we just consider this because in the absence of similar studies in this area or any other area that had the similar characteristics, and because we just didn't know that the relative importance of these layers. And with that overlaying, the final susceptibility map was developed. And as you can see here, the northern part of the railway, north of Boyd, had a higher susceptibility indexes compared to the southern part. Also, the highest susceptibility indexes were found between O'Day and Belcher. This probably happened due to the very high percentage of fens here in this basin, also because of the higher drainage density in this area, and also this section of the track is located on continuous permafrost. So it's important to notice the limitations of this map here. This map was developed based on that peatland subclasses map for the boreal plain, which was a national coarse scale map, which was not validated for this area. Also, that conceptual framework about the decreasing effect of bogs on amount of runoff and increasing effect of fens on the amount of runoff was based on the connectivity of these wetlands. So that peatland subclasses map was not considering this connectivity. As I mentioned, the Batening method can be more robust and structured. We can use methods like AHP, And also there might be other parameters that can affect the amount of runoff in this area. So after finding those more susceptible locations, in the rest of the presentation, I will talk about the second part of the project, which was hydrological modeling. I will introduce the study area, then I will talk about the different steps in methodology, and then discuss some of the results from the hydrological model and flood frequency analysis. And also I will discuss the limitations and talk about the conclusion. So I mentioned before about the importance of the water management system in this area of Hudson Bay Railway. But the effectiveness of these culverts and bridges along this railway is highly dependent on their selected design flood. This is actually the maximum flood that this structure can accommodate without overtopping. And unfortunately, the selection of this design flood is one of those uncertain steps in the designing process. And the standard approach consists of using the historical stream flow data, do the flood frequency analysis on them, and estimate the flood quantities. And in this process, we do not account for climate change effect or the process-based hydrological response of the landscape. And these are important things in the Hudson Bay Railway area. So to solve this problem, in this study, another approach has been used. A hydrological model has been developed, and it has been calibrated and then forced with climate change data to project the stream flow. And in this way, we could consider the effect of climate change. To do this, Raven Hydrological Modelling Framework has been selected mainly because of its flexibility. So there are thousands of hydrological models that can be used in this type of basins, but we chose this one mainly because it had a large library of algorithms for every single process. So one of the main problems here in Hudson Bay Railway area is limited available data. So with these algorithms from different hydrological models, we could easily change from a more data-intensive algorithm to simple conceptual one with less data requirements when it was needed. Also, we had a great control over the structure of the model, and we could also calibrate the structure, not only the parameters of the model. So we could add or remove a process to the structure, and in this way, we could test different hypotheses about the most important processes which should be considered in the structure. The study area for this part of the study was Weir River Basin, which was known for its high flood susceptibility during the last study. It was a headwater basin in the lower Nelson River watershed with a total area of 2,200 square kilometers. It was located in the discontinuous zone of permafrost in a wetland-dominated basin, and it was mainly chosen because it was one of those few basins with water gauge in this area, and also because it was unregulated natural basin. Also, this basin was near Gillum Weather Station, where we had available weather data since 1970s. So methodology in this study had different steps, starting from HRU delineation, which was based on 3 different data sets. Then a hydrological model was developed using a Raven Hydrological Modelling Framework. Then this model was calibrated and validated based on the stream flow data from this gauge here downstream the Weir River Basin. And then it was used in this subbasin, Weir River Breach subbasin. And after that, it was forced by a climate change model and a model data. And at the end, the flood frequency analysis has been done on the historical and projected stream flows for these 2 locations, the gauge location and the breach location. So what are hydrological response units? So these are the locations, these are the areas in the subbasin that have the same combination of vegetation, soil type, land cover, and elevation. These are the locations that we have a storage compartment. We can resolve the vertical water balance equation and calculate the water fluxes to and from these storage compartments. For delineating these HRU in this study, 3 different data sets has been used. The first one was North America Lake and River Routing Product, which gave us the information about the lakes, subbasins, and river network. The second one was Land Use Map, which was a reclassified and a simplified version of that peatland subclasses map. And it only had three classes: lakes, wetlands, and forests. And the last one was elevation bands, which was derived from meridians. By overlaying these three maps in the Basin Market GIS toolbox, the final HRUs were delineated, and we had three different HRUs: wetlands, forests, and lakes. So the general model structure was initially based on previous models in basin with similar characteristics. But during the calibration process, it was changed and modified for this specific basin through the approximately 150,000 simulations. This model operates on a daily time step using minimum and maximum daily temperatures and precipitation data from given weather station. And at each time step, this precipitation partitioned among various storage compartments: canopy, snow, ponding water for the forest, depression for the wetlands, and lakes and surface water. And then this water moves through this storage compartment by the water fluxes, which are calculated based on this blue processes here. The snow fraction and potential snowmelt algorithms in this model were derived from HPV model. The potential evapotranspiration was based on Hargreaves equation, and a uniform soil profile has been assumed for the whole basin in the absence of other required GIS data. In this uniform soil profile, we had a very organic soil on top, which had a calibrated thickness between 10 and 30 centimeter, then a more decomposed organic layer, which had a thickness between 2 and 2.5 meter, and then a mineral soil with a thickness of 20 meter, and this was kind of impermeable surface. And in this soil column, water could move downward with percolation processes and could move to the surface water storage compartment by base flow and interflow processes. This soil column was slightly different in the wetland HRUs. Here, instead of that organic prose layer, we had depression storage, and the outflow from this depression storage was calculated based on overflow and seepage algorithms. The rest was the same. And for the lake HRUs, there wasn't a lot of processes. It was only precipitation and evaporation, and also very simple stage discharge relation for these natural lakes. So in each time step, the water in the surface water storage compartment was calculated for each HRU, and then this water was routed downstream to the sub-basin outlet based on the gamma unit hydrograph method, and then it was again routed downstream to the outlet of the basin through the channels based on an analytical solution of diffusive wave equation. So the spin-off period for this model was from 1977 to 1990. And during this time, the model was separately calibrated. And then the initial stage of the storage compartment was calculated before starting the calibration period. The auto-calibration tool was Ostrich Toolbox. The optimization algorithm was DDS, Dynamically Decision Search, for calibrating 62 parameters. Each trial had 6,000 runs to calibrate this number of parameters. And for reducing the difference between observed and simulated hydrograph, the objective function which was used was Nysath-Cliff efficiency, or NSE. So with this setup, we calibrated model for the period between 1990 and 2014. And as you can see here in this graph, which compare the simulated and observed hydrographs for the Weir River gauge, the model had a well performance during the calibration period with the NSE of 0.72. But when we simulate the model for the validation period, which was between 2015 and 2023, the performance of the model dropped, and we got an NSE of 0.23. And as you can see here, the model was not capable of simulating the extreme events like 2017 flood. And this was probably happened due to overfitting the parameters during the calibration period. This simulation, the study period time was about 33 years, and we were using the same parameter set for these 33 years. But this was not really accurate for the study area like this, with degrading permafrost and changing landscape. So the snowmelt processes was calculated here based on a simple degree day method from HPV model. And as you can see, this simple method could capture the freshet timing, as you can see here in the mean monthly flow regime curves. It could capture the freshet timing during both calibration and validation period, but it couldn't actually capture the amount of freshet, spring freshet, especially during validation. So during calibration, the spring freshet was underestimated by 5 cubic meter per second, and this was increased to around 25 cubic meter per second during validation. Also, this model could not capture the seasonal pattern of the flow regime curves, which we have the highest peaks during spring, then lower peaks during summer because of the higher evapotranspiration and also higher storage capacity of the organic top layer. And then slightly higher peaks during fall due to the lower evapotranspiration. We cannot see this type of seasonal pattern in the simulated regime curve during the validation period. Also, the model performance was different for simulating low flows, moderate flows, and high flows. So for the low flows lower than 100 cubic meter per second, the model performed well during both calibration and validation period. But this was different for the moderate flows. During calibration, it could reasonably reproduce these moderate flows, but during validation, as you can see, the density of the points for these type of flows decreases around this line. And by saying this scatter plot for the validation period, we can say that the model is not capable of producing extreme events like high flows, like the ones exceeding 300 cubic meter per second, which were common during the extreme event like 2017 flood. This has probably happened due to the dynamic changes in the hydrological connectivity between the HRUs and subbasins in the high flow condition. So we could not simulate this changing connectivity in this model with simplified structure. This study area is located in a discontinuous permafrost, and the connectivity between these HRUs and subbasins are completely different during low flow condition and high flow condition, which is not being captured here. Unlike the moderate and high flows, winter flows were captured pretty well. The winter flows were around 2 cubic meter per second, and to adequately capture those transient parameters should be defined here for some of the processes like infiltration, seepage, and overflow from wetland algorithms. So for these parameters, two different values have been assumed, one for winter frozen condition between beginning of November and end of May, and then one for a top condition for the rest of the year. And by doing this, as you can see in the blue hydrograph here with transient parameter, we could capture the very low flow, base flow during winter. But at the same time, by adding these transient parameters, the peak flows during snowmelt season was decreasing in some of the years and during the study period. And this probably happened because of very low contributions from wetlands during this time of the year. So we assume that wetlands have frozen condition between, by adding these transient parameters, we assume that the wetlands have a frozen condition between beginning of November and end of May, which can be true for the frozen soil parameters in infiltration and seepage algorithms, but it's not accurate for the wetlands parameters, and they might contribute more to the stream flow during the snowmelt season in April and May. So after calibrating and validating the model, this model was to project the future stream flow condition. This model was forced by daily maximum and minimum temperatures and precipitation data from climate change model under SSP5 scenario. The data derived from CMIP6 datasets, and it was obtained in a downscale format for given weather station grid. And this model, specific climate model, was chosen because of its better alignment with the recorded historical precipitation volumes compared to the other climate models in the datasets. And after that, flood frequency analysis was performed on 5 different daily streamflow data using GEV distribution. So we had 3 different daily streamflow data for Weir River gauge location, one from the historical data from the gauge, one was the simulated streamflow by the model for the period between 1990 and 2023, and the last one was projected by the model with the climate change data for the period between 2023 and 2015. And again, we had 2 daily streamflow for the Weir River Bridge location. One was simulated from the model for the baseline period, and one projected ones for the period between 2023 and 2015. When we compare the results for this flood frequency analysis, when we compare the simulated and historical results for the Weir River gauge, we can see that there was a consistent underestimation of these values, different flood magnitudes for different return periods. And you can see as we go to higher return periods, this underestimation was intensified. And this was mainly because of the limited ability of the model to reproduce high flows. But when we compare the projected streamflows and simulated streamflows from the same model, we can see that there was a increase in all the flood magnitudes for all the return periods. And this means with the same model, we get higher flood magnitudes in future. And this probably suggests that flood risk is increasing in this area. And this was the same for Weir River Bridge. When we compare the simulated and projected flood magnitudes for different return periods, we see that all of them are increasing, but there is a decreasing trend when we go to the higher return periods. And also about the bridge performance, if we compare this value 144 for 200-year flood, we can see that this bridge with current channel geometry can accommodate this amount of flow. But this result should be treated with caution because of that lower performance of the model during validation, and because the model was not exactly capable of reproducing extreme flows. So the initial objective of this study was to incorporate climate change projections to assess the potential changes in the design flood at a selected bridge location along the Hudson Bay Railway. To achieve this, a series of analytical and modeling steps has been done, and each of them had their own source of uncertainty and errors, which have been accumulating throughout the workflow. So starting from HRU delineation, a very coarse scale GIS data for the land cover has been used. And also we didn't have any GIS data for soil profile. Also, we didn't have field data for a lot of vegetation, soil, and land cover parameters. Also, the evapotranspiration and snowmelt algorithms were not calibrated and validated in this model. The evapotranspiration algorithm was kind of a rough estimation based only on temperatures, and the snowmelt algorithm was a degree-gain method, not energy balance method. And this is probably the most important algorithm in a basin, cold region basin like this. The transient parameter had only 2 values throughout the year, and they were not actually changing gradually throughout the year, and this can cause many errors. And we also assumed a fixed parameter set for 33 years of simulation, which can be not really accurate for a basin like this with permafrost degradation and changing landscape. The permafrost dynamics has not been simulated explicitly, so we just assumed mineral soil with a very low permeability. And also the wetland dynamics, the algorithms like fill and spill and fill and merge algorithms, which are quite common in this type of hydrological model for these cold region basins, has not been added to this model structure. So with all of these simplification, mostly because of the non-available data, we can say that this model was not a fully physically based model. And in this type of conceptual model, it's kind of common to see overfitting during calibration period and saying dropped in NSE value from 0.72 to 0.23. So a semi-distributed hydrological model was developed here in Raven framework to estimate the future flood magnitudes at the Weir River bridge. The model performance declined from calibration to validation, which highlight the challenges in representing long-term changes with static parameters. This result emphasizes the need for improved data, adding dynamic soil and wetland processes, and also refine the land cover representation in future assessments. And also simulations under the SSP5 scenario projected increase in peak flows, indicating elevated flood risk under future climate condition. A detailed hydraulic assessment of the Weir River bridge was beyond the scope of this study, but a qualitative comparison between the projected 200-year flood magnitude and the observed channel geometry suggests that this bridge is probably unlikely to overtop under the future flow condition. And thanks for your attention.
That was a fantastic presentation. Thank you very much. While people are thinking of a possible question to ask, I'd just like to ask Adeleh, what would be the next steps that you imagine taking this research forward?
So my main next step, if I wanted to continue, was firstly change this GIS part. So first I need to consider, I need a kind of local map from HVR that shows the locations of peat plateaus, fens, and bogs. And using that in this part in HRU delineation can significantly change the result and improve the model performance. Also, I know that I made a mistake here for this timing of these transient parameters. So also changing the timing of this transient parameter can improve the peaks, spring snow melt peaks. Yeah, these two are the first main steps.
Excellent, thank you.
This is Mahfouz Baki. I have a quick question that how would you assimilate the vegetation nature that's being to be incorporated in your model? Do you have any idea? Like the vegetation patterns in these areas are different than the normal landscape in other parts of the country. But this particular vegetation patterns has enough impact or implications of covering the land, your evaporation system, and also, ultimately the flow conditions. Also, that vegetation's growing and disseminating over the time is all, filling up the basins, so on. So, how do you simulate the vegetation pattern in your formula? Have you ever thought about it?
So I didn't have a different data set about, so normally in HRU delineation, we have a different data set for vegetation. I didn't have that one. I tried to keep this as simple as possible because I had very limited data from HVR. Here, I parameterized the vegetation algorithms based on, again, the land use. So I had a different vegetation for forest area and wetland area. And the data for those vegetation came from the similar models in similar basins, mostly from studies in Liard Basin in Scotty Creek. And I tried to choose the range of those vegetation parameters based on those studies and get the final value during the auto calibration. And about how I consider a change in vegetation, I didn't. So I actually used the static parameter set for all the period and also for the vegetation in uplands. I assumed conifers forests, which are like green throughout the year and have the same kind of parameter sets throughout the year. Not sure if I completely answered your question.
Yeah, you did quite a bit how you formulated, but my question was actually to looking at what would be the future perspective on that. However, supplementary questions is the vegetation nature is being highly impacted due to forest fire and things like that with the temperature effect on it. And that carbonization of the forest fire putting on the ground, making the characteristics of the soil is being changing. Have you considered that in the model at all about the forest fire impact and carbonization?
No, actually, should be considered. So I mentioned that this model is using the same parameter set for the 33 year of calibration and validation and do not consider any changes. And I know that this can really has significant effect on the final result because we know that in this period, this area has changed significantly because of changes we can get from after the forest fires or permafrost degradation. And this was one of the limitations or errors.
Thank you very much for the questions. Once again, thank you very much for an excellent presentation. Have a great day, everyone.